Okay. Hello, everyone. Welcome to this WiNS seminar of today. And today, Assemgul Kozhabek, that I hope I pronounced correctly, who's a postdoc at Heriot-Watt University, will share with us something about complex network perspectives on human mobility, urban mobility, structure dynamics, and resilience. So now you will have the talk, and in the end, we can have a Q&A session, but people can always share questions in the chat, and I will take care of them. So the floor is yours.
Thank you very much, Elena. Haley, thank you for invitation. That's an honor for me because I joined WiNS when I was a PhD candidate. Now I'm postdoc. I'm still with WiNS, and I will continue to be part of WiNS. So I like this community and I found it very useful during my PhD thesis writing. So I'm happy to be there. Thank you for invitation again and for intro. So basically, I'm going to talk about urban road networks today. I studied it from perspective of network science. I studied from different scales: micro scale, meso scale, and the macro scale. Then I did a robustness assessment of different urban road networks. Then finally, I will talk about spread of congestion in urban roads and how I approach to model it. So basically, that's what it is. So uh, this work was conducted while I was a PhD student at Bournemouth University, where I did my doctoral degree in computer science. This work was partially sponsored by BCP Council, which stands for Bournemouth Christchurch Pool. So the Bournemouth area, so Bournemouth Council partially sponsored my PhD, so this project. Now, currently, I'm working for Heriot-Watt University postdoc. I'm still in working with networks, but I apply it for meta science. So I will talk about it closer to the end of the presentation, like how it shifted from transportation to meta science, co-authorship networks. So which would be, I think, which would be interesting for our participants. So let's start. So basically, uh, I I get interested in transportation research when I did my master degree at Warwick University in engineering. So there I was more focusing on transport capacity planning for mega events. So how uh, organizations should plan in advance before hosting the mega events like Olympic Games or big exhibitions or sports games, this kind of mega events. So how they need to approach it. So that was my research at master degree. Then at Bournemouth University, I did my PhD on kind of similar, but I approached it from network science. So I instead of looking at the planning, my focus was so what's happening with road networks, how it's different in every city. Is it different in every city or it's similar? Is it same in urban area and in rural area? So that was my focus. And I looked at, okay, so what happens if some key uh, junctions or roads will be destroyed or not functioning for any reason. So what will happen with the mobility in urban road networks? That was my approach there at Bournemouth University. So then now at Heriot-Watt, I'm applying So while I was previously uh, looking at the roads as nodes and links, where junctions where where nodes are represented as junctions or intersections, and the links are represented as the road streets itself. So now I'm looking at co-authorship networks where authors are nodes and the links are whether they have shared papers written paper together, and that is my link now. So even so, I mean, now it's like completely different area of study, but I am using the same tool. The network science, complex networks, equipped me with that tool that I can apply where it's relevant. So that's briefly about my background. So my undergrad was in applied mathematics, so it's all mm, interdisciplinary, but I believe it's very connected because without mathematics, um, I think I know that most of the networks, the people, researchers who apply network science, they might have background in social sciences, but I guess my feeling is um having a background in applied mathematics and then coming to network science is also one of the pathways that someone can choose because um, while in social sciences they might look differently to the networks, but we from applied network science we might look from this different perspective. So as an example, in my research, I look at road networks as a static infrastructure networks. So while social scientists might be interested more in communication, how information flow, so that's, I think, one of the pathways how to come to the network science. So, so also people from STEM can benefit hugely working with networks. So let's move on. So what is today's agenda? So I will briefly talk about our three main research findings, and they were published as a paper. So first we will look at multi-scale urban topology analysis. So how we analyzed road networks. Um, so then we will move on testing robustness of the that road networks. So we will simulate several perturbations that might appear in urban area. So then we will see how road network reacts to that perturbations. Um, and finally, we will look having our road network, having our urban network as a road network, then we will look how congestion spreads. So here we will talk that we used uh, SIR model from epidemiology, and it has good results. So basically, epidemiology models were already used for modeling spread of congestion, but our input was there that we integrated road network to to that model. So then I will show how our findings different to that previously applied models. So that's the agenda for today's talk. So multi-scale urban network topology. So here in this study, we looked at urban road networks from from three different levels. So from microscale, from mesoscale, and from macroscale. So here before giving details of it. So I would say that, as I mentioned, for when we say urban road networks, we take the road network of the one urban area, city, then we take each junction or intersection as a node, we treat it as a node, and the streets that connect the two nodes are our links. So that's how we abstracted road network, uh, road streets as a road network. So from microscale, we looked at degree centrality distribution between the centrality distribution and the closeness centrality distribution. From mesoscale, we looked at is there any, what kind of communities are there, and is there pattern of co-periphery in road networks? And from macro scale, we looked at different metrics, which is 9 different metrics: robustness indicator, meshness coefficient, average degree, degree diversity, clustering coefficient, transitivity, network diameter, average path length, and the efficiency. So that was our key metrics that we used for analysis. So, and what the results tell us. So we looked at 29 urban road networks, and we chose densely populated cities. So basically, the road networks that we looked at, they were mainly from India and China, mostly Chinese cities, because the one of the key criteria was looking at the densely populated cities. So, and our findings at the macro scale shows that there are high positive correlation between this, between our macro scale metrics. So, for example, meshedness and clustering coefficient, transitivity, robustness indicator, and efficiency of the network, they all highly correlate. So also, we found that degree and average path length are negatively correlated with all other metrics. And another note that finding that we would like to note that robustness indicators, urban road network has a high robustness network, robustness indicator, it also the more efficient networks. So they correlate with each other. So at mesoscale, what we found that there is high number of communities and low sign of co-periphery, but so which suggests that cities are polycentric. So there is no only one single city center that connects all the cities. There are different types of city centers. There might be one key city center, but also the smaller parts of the cities have their own local centers. So it's not only one city center. So also for co-periphery, there are different algorithms or methods to measure co-periphery. So so I will talk which type of core periphery model we used, or it also can be found in the paper if you're interested in details. So we can talk about it later. So at the micro scale, we looked at different distributions. So we found that degree distribution show lack of degree diversity. So most of the junction follow two shapes. So degrees in the urban road networks was either three links connected to one node or four links connected to one node. So that was the finding. And the Pittin's distribution show a strong positive fit to power law. So which means there are many nodes that don't play a key role in the road network, and there are few road uh, junctions or nodes that play a key role as a bridge, because between the centrality in road networks, uh, the nodes that have a high between the centrality in road networks, they play as a bridge to connect different parts of the cities. So there were less number of nodes with that high level of higher between the centrality score. So when we looked at closeness distribution, it showed left skewed binomial distribution. So in road networks, closeness centrality shows how that node is close to all other nodes in the road network. So that's in terms of multi-scale analysis of the urban road networks. So then our results we presented in terms of radar diagrams. So here you can see I presented there only 2 results, but I have 29 of them. We have 29 of them in our paper. So if you're interested, you can have a look. So there we show, so these are our macrometrics, which is like clustering coefficient, transitivity, diameter, efficiency, average pass length. So we show how that specific city performs in all of these metrics. So then we present the area. So where we say it has a bigger area, it's more robust. If it has smaller area, it is less robust. So that's findings from multi-scale analysis of the road networks. So then we now identified the characteristics of the urban road networks. Now we are going to test them for having our perturbations. So when we say robustness, we follow the definition proposed by Michem in 2010. So when they define network robustness as when network is able to sustain adequate functionality under network perturbations, when you start to remove nodes, and how your network behaves after that removal. So for robustness assessment, we had 2 strategies, which is randomly removing the nodes from the road networks and the targeted removal. So for random removal, we had 2 strategies in there. So first random point, when you randomly choose any junction and remove that. And the second random is also choose the randomly. But for random area is first junction that you remove is chosen randomly, but the next one should be the node that was connected to the first randomly chosen node. So that we called random area. So for targeted, we had 5 different centrality measures. So degree centrality, betweenness, closeness centrality, cut centrality, and load centrality. So how we evaluate evaluated the robustness of the network. So after removal, we looked at the size of largest connected component. We looked at the global efficiency, and we looked at local efficiency after each iteration. So that was our approach to test road network, robustness of the road network. So results show that when we look at the largest connected component, so between the centrality is the most effective one. So when you start remove the junctions with the highest between the centrality one by one, so that gives you the most effective attack of the road network. So your road network will be easily destroyed if you choose between routing based on betweenness centrality. Next comes closeness centrality with load centrality. I think it is predictable because these two have very similar definitions and their equations are very close to each other. So we predicted that it might have very close results. So then it was in the middle was removing nodes based on their degree, cut centrality. Then random area was more effective than random point. So removing nodes randomly was less effective in destroying road networks. So effectiveness of random distraction for both largest connected component and the global efficiency was the same, that random area was more efficient than random point in destroying road networks. And the combination of closeness, centrality and cut centrality, and the combination of degree centrality with closeness centrality gives a good balance between differences in disruption sequences. So there was interesting finding when we looked at the local efficiency. We saw that initially, when you start to remove nodes based on betweenness centrality, closeness centrality, and load centrality, actually the effective local efficiency grows slightly. Then after that, it decreases. So while for the previous two methods, there was no any rises in efficiencies, but for local efficiency, when you remove based on these three strategies, it first slightly removes, then it decreases its efficiency. So what we recommend after that, if you want to assess the robustness of road network, what we recommend? First, we recommend betweenness centrality as the first choice if you want to check the worst case scenario of your road network, and a random point random area to gain average robustness behavior of your road network. If you want to look at the local impact of your any perturbations that can happen, so we suggest to look at degree centrality and cut centrality based removals. So here, when we say going back, so we also explain what we say as a targeted or random. So we mentioned that there might happen natural disasters, or there might be any accidents on the streets. There are, or maybe mm, we give the reasons why and when we decide the road network is not functioning. So basically, when you're not able to use that specific node to go to from point A to point B, So we say that that specific node is not functioning. So there might be different reasons, like natural disasters or accidents. So that's about the robustness of the road networks. So the last part, we look at the spread of congestion in road networks. So we used well-known SIR model, so where S stands for susceptible, uh, I for infected, and R for recovered individuals. So it's the propagation of epidemics. So when we translate it to our congestion, the urban road congestion, we say so. S stands for free flow when there is no congestion, and I infected we treat it as congested when your node is already congested. So then R when it's recovered from the congestion. So that's our approach. So this is on the left side, you can see the classical SIR model. So for susceptible, first equation is for susceptible, for infected, and for recovered. But the literature shows that there is already used SIR model for urban road networks, but they use classical SIR model and they add degree. The K here represents degree of the node. So, and that specific study by Sabiri, 2020, Sabiri et al. So they say they took as an average degree 3. So as we mentioned in first part of the seminar, so we say that the road networks usually have T-shape, so degree of 3. So they use this degree of 3 here as in their equation. So, but our approach, we use not we don't use degree here. We use the adjacency matrix of the road network, studied road network. So that's our topology-based SIR model. So it's originated from initial classical SIR model, but we integrated here adjacency matrix, the topology itself of the road network. So what our findings show. So if you see the first image shows classical SIR model, so you can see that this red line shows the amount of, so we compare the performance of the model to the real dataset. So we used PEMS Bay dataset and the meta relay, so from San Francisco and Los Angeles. So, and we compare it to the real traffic data. So what classical SIR model gives us? So it predicts, it performs not bad in predicting congested nodes, but when it comes to the recovered nodes or susceptible nodes, it's not able to capture it. If you see these blue lines, so you see that it doesn't match and it doesn't come close prediction. But the model in the middle, it's average degree-based SIR model that Sabiri proposed. So where they take degree of the node as a input for their model. So you see that it performs better than classical model, but still there is a way to improve it. And lastly, it's our model. So where you see that it performs well not only in predicting congested nodes, but also in predicting susceptible recovered nodes. So that's the output of our model compared to the real traffic dataset. So I'm giving there the example of PEMS Bay dataset, but in our article we also have the outputs of that relay dataset. So if someone is interested, they're welcome to have a look. So then to see mean absolute error, if you see at the and below of the slide, you can see that this red one is performance of our model. So it red performs better than previous two models. So I don't know how I'm in time, I guess. So to finalize, so I was looking at the road networks basically, and that keeps to be my main research interest. But now I am slightly going to another direction where I'm looking at co-authorship networks and reproducibility challenges in meta-science. But the key thing here that complex networks, network science unifies these two research interests, and I use it as my how to say as my power to advance my research capabilities in both directions. So basically, that's it. And there is a dinosaur because my son is fan of dinosaurs. So I thought that keeps me, because he's one of my motivations to do research and to work in itself. So dinosaur is there to remind us about our loved ones. Yeah, I think that's it. Thank you for attention. Uh, this is my last slide.
Thanks a lot for this presentation. People are clapping virtually.
Thank you. Thank you.
You probably can
Thank you
see.
very much.
Thanks a lot. There was a question in the chat, but you answered it already. The question was
Mhm.
about SIR models, how they are used in transplantation networks, and yeah, you
Yeah.
explained it.
Mhm.
Um,
Mhm.
are there any other questions? Yes, Annie.
Hi, thank you for a great talk. I was interested in this SRI model as well,
Mhm.
and what the R represents for your transport networks, because my understanding of SRI models is that the sort of recovered nodes, in an epidemiological sense, they would have some level of immunity to the disease, whereas I can't really see. Like, would it, because you could do an SIS model where
Yes.
it goes straight back
Mhm.
to being susceptible. And I was
Okay.
wondering if that's maybe why the classical one couldn't distinguish between
Yes.
yeah.
Yeah, that's good question. And I also looked at there is also SIRS model in
Hmm.
epidemiology that also some researchers attempted to use. Because in our case, because we looking at the only one time step, we don't look like continuous. So if there is because even in my example, you might see that I am taking only morning peak. So I take only one from 6 to 12, one time step. And of course, logically, after recovering, it might be susceptible, but it's not in our approach. That might be something, uh, another way to approach the spread of congestion. But here we look at one time step, so which is morning peak or afternoon peak. So we don't, because SIS means that so susceptible, infected, again it gets susceptible, which might be already the afternoon peak. But since we're looking at one time step, so for us, uh, more more approachable and a logical way, it's to go with SIR model. But I know that there are literatures that apply in SIS model and the SIR RC model, and there are attempts to work with that. Yeah.
Right, thank you.
Thank you. And when we say infected, or when we model the node as recovered, it means like it was already congested, like it was the speed on that specific node went to the below some average degree, then it recovered again. So sometimes there is confusion how we identify which one is recovered, which one is susceptible. So susceptible means when it hasn't been congested. It at that specific node, the speed of the cars didn't went to the below of the average, or but when recovered, it means that that specific node was already infected, but now it's coming to the improving in terms of speed limit. So because we use their speed limit as the identification of the infected. So it goes to the lower than average. So then we treat it as infected.
So can it go from recovered to infected or not? Is that just because that would be the next time step?
It's next time step already. Yeah. In our case.
Yeah.
Yeah.
Thanks.
Thank you.
So you basically consider not the whole day or several days as time span, right? You consider
Yes.
half a day or the morning peak.
Yeah. Morning peak or afternoon peak. Yeah.
Yeah.
That was our approach.
There is a question in the chat from Alana saying that I'm curious about differences, if there are any, between the road networks you have studied. Are the cities similarly organized from India, China, and San Francisco?
Yes, but this thank you for the question. So for the multi-scale and robustness analysis, we looked at 29 densely populated cities, but the PEMS Bay and the MetRelay dataset was not part of it. For that data, we looked basically mainly at Indian and Chinese cities. There are differences on their performance, so we built these radar diagrams for each of them, so you can have a look. And some cities, when they have a closer scores, higher scores, they basically perform better and handle congestion better than this ones, which has a lower score for each of them, for each of the metrics. Oh, sorry, I need to plug in. So if you check, I don't know, because I had a limited time, so I didn't thought that I can include it. But if you interested, these two papers, so there are results presented there. So and also we compare there. There is a section that where compare Indian cities to Chinese cities, and what we found in terms of Chinese were well structured, so they usually there are not big difference, but they perform usually higher in all metrics than Indian cities. So that might be interesting. If you're interested, this paper shows the first paper shows the result. So let me plug in. Oh.
Okay, nice. Are there any other questions? I was checking the papers at the moment.
Yeah.
Let me see if there are any other questions. I was thinking about how you, again, like connected to the first question, how you decide if someone is infected, like a node is infected. So what would it be, the speed limit? Like very, very low? I don't know.
Yes, we looked at because we had the traffic data for Penn State dataset, Los Angeles and California, and the Met-Relay dataset. So we looked at when we can say there is a congestion. So we looked at the average, and we looked when it goes down drastically. So each city has different mm, threshold for being congested. So depending on the movements of the specific city. So because the traffic data might be different for each city. So there are different thresholds for two different cities. So when it goes below that threshold, we treat it as infected. And when it was infected and coming back to the normal speed, so we treat it as recovered.
Okay, so would it be similar to consider how many cars are in a certain kilometer per in a certain time? So what type of data do you have? You
The
have
traffic speed. We were
the
working
speed of
traffic
it.
speed.
Okay, so you have the speed of
Yeah. Every
the
5 minutes.
Okay.
Yes. Every 5 minutes for 7 days a week. So what we used. So that's a good idea to look at the number of the cars as well. But when I was conducting this data, um, I couldn't find that data which has traffic speed as well as number of the cars in the street. So it was quite challenging. But now maybe there are some data sets that can provide. Um,
Yeah, no, I was more asking about which type of data. So yeah, makes sense. If you have the speed,
yeah,
then it makes totally sense.
yeah, the speed. Mhm.
And I had a very short question, which is unrelated, but it's related to your next project, so on
Mhm.
science of science. What are you studying in that? What's your main
Uh,
focus?
so right now we're looking at the reproducibility and I joined 6 months ago, so I'm still integrating to meta science, but what I'm specifically working now, so uh, there are there is theory in meta science when they say the softness and the hardness of the science when they treat when they looked at the complexity of the sciences and my work there I work with the Web of Science dataset or Scopus dataset and look how I can apply network science and measure the complexity of that specific paper or specific study. So what I looked at is well, when they say the science might be soft or harder, they say that harder sciences, one of the example, uh, they might use different type of the references in their papers, even they are in the same field. But while social sciences, they might uh, have a diverse variety of the literature, but there are usually the key several papers that mentioned on most of the social sciences papers. So that's one of the aspects that we're looking at. So I'm looking at the co-authorship networks and the reference networks, how they differ in social sciences and the more harder sciences where we when we say harder sciences based on the theory that meta science has, it's more the computer science or the psychology, which is experiment based psychology, and biology. So that we treat as a harder sciences. When the softer sciences, we say that it might be social sciences, humanities, or so I'm working with different data set right now. Yeah, that's what I'm doing now.
Sounds very interesting.
Yeah, it is. It is some a little new thing, but yeah, I'm using the same tools.
That's really nice. If I don't see any other questions in the chat, so I guess we can close the seminar here. Thanks a lot, Assemgul, for
Thank you very
the seminar.
much. It was my pleasure.
Another round of applause for her.
Thank you.
And
Thank you.
then see you all in 2 weeks for the next WiNS seminar. Thanks a lot.